Evening, everyone. I'm Simon Hall. I'm the chair of the Engineering New Zealand Mechanical Engineering Group. So that's a technical group for anyone with an interest in mechanical engineering, open to anyone, whether they're an Engineering New Zealand member or not. Well, they're really quite, how would you put it? Quite economical price of just $40 a year. And for that, you get approximately one technical event or site visit like this per month. Of course, the site visits haven't been terribly plentiful lately, thanks to certain events. But we are very pleased to present to you this technical presentation tonight. So just as the refreshments of BYO, the health and safety briefing is as well. You know how to get out of your own premises. So on to our speaker tonight. Thea Jones is one of the co-founders of Astrix Aeronautics, which is a startup that was spun out of the Auckland Program for Space Systems competition, and now produces power generation devices for satellites. So after I've handed over to Thea and she's delivered her presentation, we'll then hand over to Ryan Leyland, who will be taking your questions and presenting them to Thea. So without further ado, welcome to everyone, Thea Jones.
Hi, thanks for having me. So I thought I would start off really simple for this to get us all on the same page, and that is just kicking off with a really simple question. What do satellites actually do? And so I'm sure you guys are really familiar with the famous NASA satellite builds, such as the Hubble Space Telescope. And this has been in operation since 1990, and it's used for public use of astronomy, and also as a vital research tool. Another classic set of satellites are the Landsat satellites. And so its purpose is to monitor the Earth using the Earth's varying landscapes and look at the long-term impacts that climate change on people's lives. So what we're used to seeing in space is typically very large satellites that are roughly the size of cars to school buses, and they have a lifetime minimum of 10 years, but they're expected to continue working for 30+ years. And so we can see satellites being used to solve some of our greatest challenges, but gradually satellites have become more ambitious as they're also getting smaller and much more efficient. And this is also seeing that people are now taking advantage of launch costs being more affordable, and also just being able to access space more regularly as we have more launches that occur more often. So we've taken a pivot to what's called new space now. And new space is emerging, and rather than typically seeing one large satellite that is very expensive, it costs millions to build, we're now seeing fleets of hundreds of small satellites that look just like this. And so these are called mega constellations, and now these satellites are roughly the size of a shoebox. So you have hundreds of satellites that work collectively on a mission, and the problems that these satellites now face are mass and volume constraints, which all lead to power starvation because you have less surface area to store your solar cells. So put really simply, when you don't have enough power, it means you also can't extrapolate as much data. And so that's what specifically this is what me and my team work on. And our solution is a simple and reliable way to deploy a large surface area of solar cells using inflation. So what we are typically seeing in the moment in the space industry is, because we're used to having these large satellite builds where you would expect your power systems to be running for minimum 10 years to 30 years, what they do is they build gallium arsenide solar cells. And so these are extremely efficient, low mass cells, but each of them have to be handmade by a specialist in a lab. And so what you see are these extremely high costs from labor, and they're not as well needed in the new space industry at the moment. But the struggle that we've had with moving back to non-handmade cells is we have very large, bulky mechanical systems that when you end up using commoditized solar cells or simply silicon solar cells, it adds too much mass and too much bulk to the structure, which is the reason that they haven't been pushed back in the industry, despite it being a really strong preference. So yeah, what we build is a device that we're calling Copia. So we build the lightest solar arrays for satellites. And what we've been able to identify are two really strong problems. So the first problem that you see for satellites is the limited wingspan that they have when they're really small. So what we've done is, or probably where I should start, is typically what you see is with mechanical deployment systems, they rely on multiple hinges and springboards to push out a large surface area of solar arrays. But this also creates multiple points where this can go wrong, and they typically have really high failure rates. And the second issue that you have when you try and push out a large array is the cost of the solar cells adding up with the gallium arsenide cells become really expensive really quickly. So per watt on the system in the industry right now would cost typically $2,000 to $3,000 per watt. And so this is an extremely high cost, especially when you have a very small and mass manufactured satellite build where you are building hundreds of satellites collectively together. And then when the power systems aren't able to meet this rate of mass manufacture, the costs add up really quickly. And so what happens at the moment in the industry is to keep the expenses down, we see lower power outputs, which also means lower mission times. And it reflects in just having lower functionality for your satellites. So when we look at synthetic aperture radar satellites, they typically generate $51,000 per minute of operation. But when you are limiting your operation time to charging your satellite, they're only able to turn it on in space for 5% of the time that's in orbit, which is a shockingly small amount of operation time. So what we've done is we've moved to inflatable deployment systems, and we've also moved to utilizing silicon solar cells. So we're able to achieve this at 15% of the cost of what you usually see. Yeah, that's what, also the way that this array works is we use a controlled gas system to push out the solar arrays. So inflation in space already exists, that's not new. The reason that it's not popular or not common is because in the past it's been difficult to control. And so that's something we've solved by using a system to encourage the inflatable pathways to follow in certain directions to push out the entire array, and use a UV curing system to rigidize the system once it has inflated. So we're able to safely push out the device on command, and then once it's rigidized, deflate it so that we don't have any unpredicted inflatable things that would occur. And so we're able to produce a lightweight replacement for the mechanically deployed systems and utilize the silicon solar arrays that are much more preferred. when we started trying to solve the power system dilemma in the new space industry, when talking to a lot of aerospace engineers, they made it abundantly clear that this power dilemma was mostly about price, time and production delays, and simply the bottleneck with gallium arsenide cells in general. And so they'd say things like, don't come back with something, better come back with something that doesn't give us the same price and time issues that we've experienced so far. So alleviating the bottleneck in this industry is really big, and sunlight missions that weren't possible now become viable as we're paving this way for technical growth and development of satellites for their mission objectives, and being able to provide them with power systems that can meet the quantity of satellites that they're trying to push for at the moment. And so the need for gallium arsenide cells aren't relevant anymore, as they, small satellites only have a lifetime of 2 to 5 years, where they try to replenish their satellites, or at least half of their satellites, yearly. So what we're doing coming up is we've received funding earlier this year from Rocket Lab, Outset Ventures, K1W1, and also Icehouse Ventures, with the goal to launch our satellite into space now in March. So what we're looking in this proof of concept launch is we'll be receiving a video of it deploying in space. And also we'll be able to take the temperature, pressure, and power measurements over over a few days worth of orbit. So yeah, thanks for listening. Do you have any questions?
Well, because I can, I'll just pipe up. Thanks. Do encourage everyone else to put their questions in the chat panel, please, and we'll work our way through them. Yeah, I was fascinated to hear that you're using inflation. That sounds like a really tricky thing to do in a vacuum. Maybe just conceptually, but
it actually, because you require a lot less gas storage in inflation as well. Doing inflatables in vacuum is really tricky, because you've got to be really pedantic about looking at your system and opportunities where there could be leaks. And also the biggest problems that we've seen other companies have so far is how to seal your system. So looking at what NASA did with Echo 1, they used sublimation. They used benzoic acid, which is like a sublimating powder, and they basically painted it all over the inside of the Echo, which is a really large reflective balloon, and they just relied on putting the benzoic acid in all the creases. But what they saw was buckling, where it would inflate faster in some areas than others, and then you would just see the whole thing burst. And that's what happened within an hour of it being in orbit. So it's been problematic in the past. It hasn't been so problematic for us so far. So. Oh, James, the inflatable mechanism, is it a one-time device, or do they need it to operate multiple times? It inflates once. So what happens is you have, I'll just go back. So what we see, are you able to see my mouse by chance?
Yep, yeah, we can see that.
Okay. So what happens is you have these two solar arrays that are folded up in both of those and the gaps outside of the internal gas storage here. And so on command, when the satellite is in sun, what we do is we use pyro cutters to trigger the doors to open and push out the arrays. And so what I can't show you is the inflatable system on the bottom of the array, but you wait for it to push out in basically the X and then both ways in the Y direction. And then once it hardens, it stays out. We're not able to retract it back yet, but that's also not usually done for solar arrays.
Somebody's asked if they recycle satellites that reach their lifetime. I suspect the answer is no.
Unfortunately not. Especially smaller satellites once, so when they deorbit, they come down from low Earth orbit and they burn up on re-entry. I actually do know someone who is also in a startup called SpaceForge. So Joshua Weston, he makes reusable satellites, but what the purpose of the reusable satellites for is you can manufacture certain things in space that you just can't quite do in a lab. And so he puts that in the satellite, it goes into space for 6 months to a year, and then on re-entry it burns through these like heat shield protections and they're able to save the satellite basically. But that's a very difficult process that isn't usually done. Yeah.
Somebody says, what pattern does the folding out inflating follow, and how actually does it work? It'd be lovely if you had a TV show of one of these things unfolding. That's what I was really hoping we would see.
Our patent is nearly done. If this was in a few more months, I'd be able to show a video. But we have basically what I can describe is we have, for the ratio of surface area, it is like a 1:3. So there is like inflatable pathways running underneath the device, and for like a certain area, there will be pathways versus areas that don't. So we've been able to, the way the pathways are designed are to push it out in one direction prior to pushing out in the other one, if that makes sense. That's as much as I can say. I apologize. I'm really excited about it. I love to talk about it, but I can't.
So are there a whole lot of tubes at the back of the array that inflate and straighten out? Is that the basic principle?
Yes.
Yeah.
Clever.
Simple and clever.
Simple is preferable in space. No one can go and fix it once it's up there. So
James wants to know what the inflation pressure is low. Just how low? Does it get as high as that?
It is low. I don't know exactly how many pascals it is. My engineer would be able to tell you exactly how many right now. Other than giving you an exact number, I'm sorry, I'm not quite sure how to answer that.
Yeah, but is it around about atmospheric pressure or a lot higher?
It's roughly just sitting a little bit above atmospheric pressure. It's not much at all.
Yeah.
Yeah.
So you haven't got an atmosphere, that's quite a bit. And next question is, what is from Rick? What's the dollars per watt for your solution?
So currently in our early stages, we're able to provide this at $500 US per watt. So once we're able to begin mass production, that would hopefully lower a lot more. But that's where we've started from being able to sell. And we're actually working with Fleet Space at the moment. So they're our first commercial flight that is going off in December 2022. So, yeah.
And James wants to know if the array is glued in place. If it opens, does it lock itself, or does it just stay inflated and that's sufficient? Or does it no longer matter if the tubes are inflated?
So the did you say the array is fixed or glued in place? Oh, I said neither. Sorry, to answer that question, what happens is the array itself will harden with a UV resin, which is like a very liquid type substance that hardens when it is exposed to the sun. And once that happens, we actually release the inflation ourselves. So the internal gas storage system that you see as well will trigger for it to open and release the air pressure out. So it will only actually be inflated for the first like 2 minutes, and then it rigidizes, and then the gas is gone. Yeah, I'm not sure if I answered all of James's question.
No, I think it's very satisfactory. And you've answered Rick's question, what provides mechanical rigidity. So you've got an ultraviolet sensitive material that locks up when it's exposed to ultraviolet light. Any extra problems for space junk from Ross Galloway?
Everything, so satellites, it's mandatory to have some form of like deorbiting thing on it, whether it's an electric propulsion that's going to push it down to deorbit, or whether it is an electrodynamic tether that will interact with the Earth's field and pull it down. Because our device is able to push out a surface area so large, it creates a drag force that actually helps it deorbit a lot quicker. So that is good for space junk. But also the everything on the device is either glued, heat sealed, and then laminated in some way. So there's no possibility for like a solar cell to break off and fly off and become space junk, if that makes sense.
Everyone wants to know what, sorry. Are the cells printed onto the fabric? Are they silica based? I think you've already said they're silicon cells, aren't they?
Yes, they're silicon cells that we use. So we both will glue, heat seal, and laminate the cells to the process. So also something that we do is something I didn't mention as well was usually cells, well, gallium arsenide cells require a special cover glass, or and so for silicon cells, no, that doesn't quite properly exist yet. So we use a range of transparent materials as cover glass to extend the lifetime that they will have when exposed to radiation. So that's also hence why the lamination process as well. So yes, we stick them down thoroughly.
Are they steered to point towards the sun the whole time, or not? They just pick it up when they...
Yeah, that's very mission dependent. So you can put your satellite into a sun synchronous orbit, and basically it will be in the sun 24/7. And you know, obviously when it's perpendicular to the sun, it's generating 100% of the energy that we would expect from it. Even when it's not, and it's off by some sort of degree, what you just see is a lot more reflection occur that is also normal for solar arrays. So it would just be less power than that. And also in low Earth orbit, your satellite gets exposed to an eclipse, for the ratio is roughly like 1 to 3. So it would spend 3/4 of that orbit in sun and 1/4 of that orbit in eclipse. So it does get a lot of sun time.
Yeah, okay. Jackson's wondering how you produce the gas. Is it chemical reaction or pressurized?
Pressurized, and we store it in the canisters.
Just a little. How big is the canister?
Oh, it's small. It's does anyone have Apple AirPods? It's like this, but cut in half and then stacked on top of each other. Like it's roughly the size.
Emir wants to know what temperature gradients occur in these arrays and how much are they able to withstand thermal stress? They must get major thermal stresses.
Yeah, so this prototype, this proof of concept that we're launching or building for right now, at its highest, it's able to withstand 150 Celsius, and at its lowest, -80 Celsius. And so that's what this proof of concept is being built to withstand. And that's just because of the orbit that we've been given to meet the requirements for.
So have you emulated the space environment in your lab for testing the inflation mechanism? Have you got a little vacuum chamber?
We do have our own vacuum chamber. It's a little bit, it's super DIY. So we used it for rapid building. And then when we need to do a proper test, we go to Rocket Lab and use their vacuum chamber there. So we've been able to do an insane amount of vacuum tests to make sure that this is ready prior to going to launch, and also thermal cycling, vibration table, and a few other things. But the test in space is going to be the ultimate one.
I'll bet.
Yeah.
So another question from me: how does this array unfold? Did you get into origami or something like that? There's an unfolding technique.
It's basically origami if you think about it. We actually before we built this version, which is to be a really large flat 2D array, we were actually looking at building a really large sphere that would have a Fresnel lens and thermionic electric converters on it. And so we had a far more difficult time folding up a large 3D object, and basically we took the entire sphere and folded it X, Y, and then Y at Y side at each and every point, and then made the Fresnel lens basically pull out in the center of the sphere. So we kind of started off trying to fold more horrific things before this one. So yeah.
I'd love to see it.
This design is nice.
I'd really love to see it. Yeah. How do the grams per watt for silicon compare with gallium arsenide from Rick?
So this, when seeing gallium arsenide solar cells on a mechanically deployed system, the #1 in the world building that is MMA Design, and they got their power system to be 140 watts per kg. Using this design, silicon solar cells, we were able to get this 160 watts per kg, so a higher watt per mass, if that makes sense. And the only trade-off experience that you will have is our one will have a much shorter lifetime of 3 years, which is suitable for small satellites. And we can't scale this to large satellites yet. And that's what MMA design is able to do with their gallium arsenide and mechanically deployed system. So
in Ling Ning presumes the power only generated when the satellite is facing the sun. So is there a battery to store the power for when it's shadowed? There must be.
Yeah. So we just provide the solar arrays and not the battery, because every single mission is so different. They prefer to pick their own. Yeah.
Andrew Campbell wants to know if you test each array on the ground before the launching the satellite. That's presumably
100 times.
the whole
so many times. Yeah.
Yeah. The whole unfolding process and everything.
Yes. So we will watch the array deploy in a vacuum chamber, put it through the shake and bake facilities. So thermal cycle it, try to basically kill it with all of the testing facilities that we have. And if it survives all of that, then it can survive space and we're happy to hand it over.
And you have to keep it away from ultraviolet light, presumably.
Yeah, we put that system on last.
Okay.
Otherwise it becomes very difficult.
Yes. Yeah. Yeah, so James is talking about the UV cures, and I think we've covered that.
It does look like a butterfly. Yeah, it does.
Yeah, it would be. I missed the first part, but why is the lightest compared to other systems? And presumably because you've got tubes rather than mechanical bits.
Yeah, so everything on that you see in this image basically sits on some plastic and simple. So you just have your mylar and kapton, and you have the someone's doing origami now. That's fantastic. Sorry. So you have, because we're able to use silicon solar arrays, silicon solar cells, they are much thicker and sturdier than gallium arsenide cells. So that bulkiness that you would typically see in a mechanically deployed system, they make up for because gallium arsenide solar cells are so easy to break. They're like as easy to break as rice crackers. And so a lot of that bulk comes to, you know, building and reinforcing that it will stay not broken, that it won't break, sorry. Yeah. And then we don't have to worry about those kinds of small engineering design concerns with silicon solar cells. And yeah, we don't have any hinges or large booms or things. It is plastic.
And what Rick wants to know, how immune they are to a solar flare that presumably kills it along with every other one.
Yeah, they have a hard time. We're going, next year, we are doing a lot of longevity and yeah, basically just longevity testing, especially with the cells. So from what we understand, the silicon solar cells so far have a lifetime of roughly 3 years, and they are able to operate at like 17% efficiency, and their degradation rate is a lot quicker, which is why they can't last for 10. So by the end of its lifetime, we'll probably see roughly 60% of, you know, it's maintained 60% of that efficiency. And we don't know what will happen to them with a solar flare. We will see. We will see when we put it in one of those chambers.
Yeah, they're a bit hard to organise, aren't they?
Yeah, also being stuck in New Zealand doesn't really help. We would have liked to be at ANU this year, but it's okay when that happens.
I'm just going to button here because I don't seem to have an option to type in questions. What sort of time are we talking about to unfurl? Like, is it sort of a thump, or is it sort of like this graceful sort of thing?
It will happen within roughly 20 seconds for this model that you see in front of you, which doesn't sound very long, but it is a slightly more graceful, slow inflation. So yeah, no, we don't want to bunk. That's worse. that's worst case scenario for us, actually. So yeah.
And Andrew Jackson, how many of the cells are connected in series, and how much redundancy is required in case of you lose a cell?
So in this, what you see is it's in series, column-wise and in parallel row-wise, but each cell has a bypass diode. So let's say that you have, you know, like tiny, I don't know what's in space, is a stone or piece of debris that shoots through one of them. It should still go through the system. Sorry. Yeah, that did make sense. So it'll still work. And even in a further worst case scenario, if this collides with another satellite and half of the wing is ripped off, you should still see power come from the other half of the wing that's left.
That's impressive. And what's limiting the life to 3 years, again from Andrew Jackson? He assumes it's
that is the solar cells. Yeah, the solar cells being exposed to radiation and just atomic oxygen. So it kills it really damn fast. And that's why it only has a lifetime of 3 years. It'll still be operating after 3 years, but the efficiency level will be so low that we don't consider that alive anymore. So.
Well, that seems to be the end of the session. I've got one more question. Who is it that folds them all up into this incredible, like an incredibly skillful job?
Max and Will, so my other two co-founders, it takes two of them to do it at once together so far.
Yeah.
And so we vacuum suck them. So we attach like a vacuum pump to
the piping.
Yeah, to the piping basically. And once it vacuum sucks it, the array becomes much thinner and much smaller. And so it's actually really easy to pack it back up.
There must be knowing which fold to make next must be
quite
complicated.
You have to do it in the right order.
I'll bet. Well, I think we've come to the end of the questions. So I think it remains for me to thank you very much for what seems to be a really brilliant development. And we're certainly waiting with bated breath to see the results of your first space exercise. And I'm waiting with bated breath to see a TV of it unfolding.
I can't wait as well. We're all so excited about it.
You said it. I can't. It's not fair.
I know. Thank you so much for having me.
Anyway, thank you very much. It's been very interesting. And I'm very impressed with what you're doing. And I'm sure everybody else is.
Yes, indeed. Thank you, Fia. Thank you, Brian, for wrangling questions, and also big thanks to Holly for her behind-the-scenes wrangling of the Zoomery. So this is probably our last MEG event for the year, but do keep an eye on your inbox. We may find another thing to entertain and delight and educate you, and otherwise. We'll pop up again in the new year, hopefully in a different traffic light level and with some in-person events.
I hope the bloody things have all gone.
Yeah.
Okay.
All right. So thank you, everyone, and good night.
Good night.